Sorry, I didn't Lindsay said no one in. They're not here yet, they're still in cover, now she won't use.
Okay, people, it's question and answer day. I'm staying up here this time, so if you've got questions, I'm pretty sure other people in this room will have the same question. So please ask away, and we'll do things either that are those questions or are very similar to those questions. Talk to me. And a hush falls over the crowd. Yes, Adam.
Adding 2 or second to 2.5.
2532. So let's take a look at a similar problem. Would you like to look at 31 or 33? Okay. 31 says f of v, L of v, the question asks, using the theorem 4, 5, 7, and 9, explain why the function is continuous at its domain, right? So let's start with what's the domain of this function? So what numbers can I plug in and what numbers are verboten? What are forbidden? Let's start with that piece on the left, v. It's just like f of x equals x. What numbers are you allowed to put into that? Everything. So the domain, at least of that part, is minus infinity to infinity. Yes? Now let's look at the other piece. The other piece is a composition. There's one function inside another. So I'll start on the inside. Think about 1 minus v squared. What's the domain of that? Jordan. Say again? Because
the inside of the natural log must be.
I'm not dealing with the natural log. Just look at ln of 1 minus v squared. Just look at the 1 minus v squared part. Just that part, you said the domain is all real numbers. Why is the domain of that all real numbers? Because it's a polynomial. I can plug anything I want into polynomials, right? That's a quadratic. As soon as I write that number down, write that word down, polynomials, my brain goes, one of my theorems says something about polynomials. Which theorem says what about polynomials? 7 says what? Aha! So these are continuous at every number in their domain. They're defined everywhere. by theorem 7, those are continuous everywhere. But I still have to take care of that ln. Again, according to theorem 7, what does theorem 7 say about logarithms? They're continuous on all values of the domain. Theorem, I can spell 7. So now I get to ask the question, what's the domain of a logarithm? Things that go into a logarithm can't be negative, they can't be 0. So according to this, stuff must be strictly bigger than 0. Wait a minute. In our problem, we have that. I just came into a restriction. Now, there are 3 different ways you can do this. You can do this algebraically. In order to solve a polynomial inequality, algebra class, chapter 9, 10, somewhere back there, section 4, 5-ish, we did inequalities involving polynomials. First, you set it equal to 0, and then you figure out what's going on in between, right? So I could do this algebraically. Where is 1 minus v squared equal to 0? Go ahead, Evan. But there's more. What other option could I have for v? I could have -1. Now, those are the only places it's equal to 0, which means everywhere else it's either positive or negative, right? It can only be 0 at those 2 spots. Everywhere else it's either plus or minus. So pick a number smaller than -1. -2. I'm going to write that number right here, put it in a little box, plug that in to my function 1 minus v squared. When you put in -2, what do you get? Negative. That's what I care about, the fact that it's negative there. It is -3, but all I care about is it's negative. Pick a number between -1 and 1. Do it again. A number bigger than 1. I want to know where it's positive. That's between -1 and 1, not including the edges, because the edges are where it's equal to 0. Now, the rule we had up there, theorem 7 said logs are defined on their domain. The domain is where the thing inside is positive. That's this spot. That's really theorem 9, because theorem 9 says if you have one function inside another, you need to use the restrictions from the inside to tell you about the outside. Now, I've got the W piece. I've got the logarithm piece. What was the domain for our W piece? I'm sorry, V, not W. Where the hell W come from? Wrong problem. V. What was the domain for our V piece? All real numbers. And then what am I doing with those two pieces? What operation? I multiply those two pieces, right? Theorem 4 tells me what happens when I multiply. Ladies and gentlemen, if you are all having conversations, I can't. Please. I want you to be paying attention to this question. If you've got a different one, we'll get to yours in a minute. If I'm multiplying the two pieces, I need to look at the restrictions. If f and g are both continuous at the same place, then f times g is continuous there. This piece is continuous everywhere. This piece is only continuous here. Where are they both continuous? Only on this part. So that means that this, by theorems 7 and 9 and 4, this is the region where this whole thing is continuous. You see, I had to piece together all the different rationales. This is like the geometry class we took in high school, where I had to give a reason for each sentence. The reasons in this case are this is what this theorem tells me. This is what this theorem tells me. Better, Evan? Wonderful. On this or something else? On this. Talk to me, Jonathan.
Explain some of the areas why the function is continuous. Okay, so will we just say that it's a polynomial?
Well, this part was a polynomial, right? And this part was a polynomial. But as soon as I did logarithms, I had to say, oh, what's the domain of a logarithm, right? And then I had to put it together and say, what's the domain of this whole thing? And that's really what theorem 7 tells me.
Is there one minus one plus b squared without changing?
It would change what we do right here, doesn't it? Exactly. It would definitely change the domain. The logarithm itself tells me that the interior part can't be negative or 0. Jordan. More questions. Who's got the next question? Yes, ma'am. Number 52, that's the one I was drawing the pictures, right?
Yeah.
Okay. So, what are we told about our function in that problem? F is continuous on all of 0, 1? We're told two other things, right? And now, what you're asked to do is to talk about the intermediate value theorem. The intermediate, so let's go read the intermediate value theorem together. What's the intermediate value theorem say? Evan.
If f is a, b, and f of a does not equal f b, periodical, you end to f of a and f b, there was an x value of f b equals n.
So somewhere between 0 and 1, there should be a value c, so that f of c is equal to 2. Because 2 is between 1 and 3, and 1 and 3 are different. That's only true if my function is continuous. It's only guaranteed to be true if my function is continuous. But what you're telling me now is the function is not continuous. So here's the picture I have in my head based on the information you've given me. f of 0 is 1, f of 1 is 3, right? And n is equal to 2. Two is definitely between 1 and 3. I'm good with that part. The question says, sketch a graph where the conclusion of the intermediate value theorem is true. The conclusion said, Evan, that there would be a value between 0 and 1 where we hit that green line. So I want you to draw me a function that hits that green line and is not continuous at a quarter. So right here, here's 0.25. I want you to have something that makes it not continuous. What things make a graph a function not continuous? An asymptote, a hole, a jump. So you need to have a hole or a jump or an asymptote on that vertical line. But I still want you to hit the green line somewhere. That's picture 1. Picture 2. Draw me another graph that misses the green line. All you have to do is figure out which way the picture goes. One of them hits this line and still has a hole or a jump or a gap or an asymptote over a quarter. The other one misses the green line and still has the jump, hole, gap in the same vertical location. I can only guarantee it's going to hit if I know my function is continuous, because I have to connect that dot down there with that dot up here, and I've got to cross the green line somewhere. Which means I could lift my pen, right? So if I lift my pen, I have the option of missing the dotted line. It's not a requirement, it's an option. So draw me a picture that works both ways. Draw one that hits the line, draw one that misses the line. But make the jump, hole, gap occur when x is a quarter. This is the best part about a theorem. A theorem has a bunch of ifs. If all of these things are true, then this thing has to be true. Think of a theorem like a playground slide. If you go up the ladder and the theorem works, you can slide down to the bottom, right? Can you get to the bottom if you never go up the ladder? Sure, just walk around the damn slide. If it's not continuous, I can still get to the bottom of the ladder, bottom of the slide. I just don't go up and down, I just walk around. So there is still a way for me to hit the line. There is still a way for me to miss the line. Draw pretty pictures that one does each. Better? Wondering. I saw more hands. Give me more questions, people. Keep talking to me. Yes, sir. Graph of number 6 from 2 point. Okay. So the whole idea is for us to try and fill in the graph based on what they tell me, right? So do you want to look at number 7 or number 5? Okay. Number 7 says, limit as x goes to 0 is infinity. Limit as x goes to 3 from the left is negative infinity. Limit as x goes to 3 from the right is positive infinity. Limit as x goes to minus infinity of f is 1 or negative 1? 1. And in the other direction, it's negative 1. Okay. I need to draw one picture that obeys all 5 of these rules, yes? I have limits whose output is infinity at 0 and at 3. On my graph, I should see vertical asymptotes there. I have limits as we go out to infinity. I should see horizontal asymptotes there. But the one on the left and the one on the right are different. I will learn to live with it. Let's draw a picture and just put in the asymptotes. I know I will have a vertical asymptote at x equals 0. I will have a vertical asymptote at 3. On the right side, when x is going to positive infinity, I'll have an asymptote at -1. I only care about that on the right side. So I only put part of it on the right side. On the left side, my asymptote should be at 1. With me so far? Okay. Tell me what's going on at 0. What is my limit as we approach 0? And it says from both sides, right? So that means on both sides of the y-axis, I should be going up. Hey, wait a minute. What happens if I keep going left? But as I keep going, it's going to eventually settle to 1, right? It could go under it and come back up. It could go back and forth a bunch. It could just kind of slide down like that, right? It could go under and back up and back and forth, right? As long as it eventually settles down, it could go under, stay under, and then turn back up, right? All of those work for that side. What's going on at 3? Here. I have a different limit on each side, yes? So what's happening as I come towards 3 from the left? So I should be going down here. But I'm up here, right? So as I start to go over, I should keep going down somehow. Now the curviness is up to you, but it shouldn't go back and forth on itself. It could go up and down a little in the middle, but it should go down as I get closer to 3. What about on the right side of 3? It says positive infinity, right? So I should be going up there. What happens as I go all the way out to the right? I get close to -1. Again, I could do all those different options over there. I could just slide down towards -1 and never touch it. I could go under it and come back up. I could wiggle back and forth. I have to account for all of the asymptotic behavior that those limits tell me about, and then just draw one picture, fill it all in. Over here, I just want one of these. You can pick which one you want. Make sense? Wonderful. More questions, people. How do I know when?
You said I can go through the asymptote as long as it settles.
Yeah,
How do you know the difference between that and like an oscillating function?
that is an oscillating function. If it's wiggling back and forth like that, that's what oscillating means, right? It's just slowing down as it oscillates. Who's got a lanyard for their keys? Anybody in this room? Can I borrow your lanyard for a second? Who's got a lanyard with them? Pick it up, put it on my finger. I'll bring it right back in. An oscillating function, yes? Straight up and down is my eventual behavior. If I don't do anything, it doesn't move, does it? Isn't it eventually going to end up there? So it oscillates back and forth, but eventually comes to rest straight up and down. It oscillates back and forth and keeps getting closer and closer to this perfectly vertical position.
But it will never.
Never truly, exactly. If you think about this pendulum, right now, when I'm not doing anything, isn't it wiggling just a little?
Yeah.
So it's just barely moving, but it is still moving. It's not truly at straight up and down. Thank you very much. My favorite idea of this sort of settling oscillation is the shock absorber in my car. I've driven through Pittsburgh. It's not pleasant. You hit a bump, what happens? Boingy, 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 boingy. Well, but eventually your ride settles out again, doesn't it? So it slows the oscillation. In physics terms, we call that damping. And if you take physics 2, where we talk about wave behavior a lot, we'll talk about damping. If you take differential equations, we'll talk about critical damping and all sorts of other behaviors. Oscillatory chemical reactions behave the same way. You've seen color change reactions in chemistry? Same deal. Useless crap. We're never going to see, oh my God, do we see this everywhere? Music, sound, echoes in particular, are all dissipating vibrations in that same fashion. More questions? Yes, ma'am. Yeah.
When it's y equals something,
Y equals a number.
it's on the x-axis, but when it's x equals something, it's on the y-axis.
Choke, cough, gag, sputter. Not really, because if I say y equals a number, right, if I say y equals 3, where do I put the 3? On the y-axis. I draw my line parallel to the x-axis, but it's not on the x-axis. Okay. But that's not what you said, and this is another case of me going, I think I know what you mean, but that isn't actually what came out. And if I horizontally, yes.
And so for x, it would be on the vertical.
Exactly. Doesn't help if I draw it off the bottom of the screen and you can't see squat. I know I sound like a pain in the ass, Nicolina, but the whole point here is for me to understand, really, I know what you're saying. I want you to communicate it well so that somebody else who isn't me would be like, oh, okay, that makes sense. More questions. Which section? 14.
All under the practice. By the time you get to like 9 times the limit is x equals infinity of x. What do you do from then on? Can you then compare the coefficients like in that last step?
Yes, you could also use all of the intermediate laws where you're like, oh, I've got division, right? So I can take the division and do the limit of the top and the limit of the bottom. And then I can do my 1 over x to the whatever, yes.
It goes up to x cubed, but it's square root.
Right.
Can you still use like cube root of x? Or something like that to remove the x cubed or the x.
It's under a square root, right?
Yeah.
So I think my best bet to use to remove is to use a square root of an x cubed. You said it was an x cubed under the
One. Oh, you just.
by putting it over itself. Absolutely. Or I could say I've got the square root of a bunch of stuff, right? I could do the multiplying in here, inside the square root already. So instead of saying I'm gonna multiply by this on the outside of the square root, I can multiply by 1 over x cubed, 1 over x cubed inside the square root. Isn't that multiplying by 1? You can multiply by 1 anywhere you want because multiplying by 1 doesn't change things. More questions? Yes, ma'am.
Thanks. Part A, as you're looking at the graph and seeing where the limit is towards, positive, infinity. And I didn't know if the asymptote at 2, the vertical asymptote at 2 affected the limit to infinity at all.
No. Once you are looking at limits to infinity, you can ignore all the stuff in the middle and just look at what happens as you go out to the edges. Angela, you had your hand. Okay, hang on. 14, which section? The same one? I'm looking at the wrong page. That's why I'm having trouble. So yes, on 14. That one?
Here's like. And
Yes. Well, you can think of a root as a 1/2 power, right? Yes, then you can use the power rule. Because those are interchangeable, fungible, then yes, you can swap out one rule for the other. Because a root and a power are really the same thing.
I think that we included all the correct ones.
Did you get the right answer at the end of it?
Like you're to the like and justify them.
Then I just want to know that when I'm done, I agree with the things you've justified. Did you use every exact little bit? How detailed and granular do you want to be? I want to know more or less you know what you're doing. I'm not going to go through, oh, you forgot to use limit 5 as well as limit 4. I used the right thing in the long run. I'm good. Just tell me you know why it works. That's the key difference. If you've seen calculus before and you're looking at this and going, I don't remember any of this, it's because your calculus teacher taught you how to do calculus. And that's great. If you take it on 100% faith that I am the voice of God. People, I am no way near the voice of God. So why does this work? I don't want you to believe me. I want you to be able to believe you. Justify your answer so that you know why this worked the way it did. By the way, if you continue on in calculus, you'll do a lot more how. If you continue on in math in general, you'll do a lot more why than how. That's what science is all about, the why. Engineering is about the how. Yes, Dave.
No, I'm 2.6, remember? I multiply by the conjugates.
Okay, good.
And I, simplify from there.
Lots of algebra.
I got to get square root 4x squared plus 3x minus 2x.
Yes.
But then I kind of didn't know how to simplify for
The important thing in this problem is the fact that our limit is going to minus infinity. Right? Now give me the thing you said you'd simplified to.
squared plus 3x and out of the square root minus 2x.
So here's the deal. I look at this and I say, what's the highest power of x? Except that square is under a square root, and those cancel each other out, so it's x to the 1. So I really want to do that. Right? And I'm perfectly fine when I try and put that with this, and when I put that with this. But when I go to put that with this, I have a problem. This doesn't have a square root, that does. So what did we say yesterday we could do to fix that? Well, there's just one problem with what I've just written. I agree with you. That looks like 1 over x. But this root symbol means take the positive square root. And that makes this a positive number. Because we're going to minus infinity, our x's should be negative. How do I fix that? Boink. Ta-da! Now I can proceed with that limit. When I combine those two pieces, this extra minus sign will float around out front. This only is something I have to worry about when x is going to minus infinity. Otherwise, square root of x squared is positive, and that's perfect because we're getting positive numbers. But when I'm putting in negative numbers, I have to account for that negative in this symbol. Yes?
Is it negative?
Yes. Well, because x and 1 over x will be fine with each other. See, this is not in a square root. I don't have to worry about any of this garbage. This one's in the square root. I have to worry about it. In one sense, I want to make sure that what we do not just is algebraically correct, but is algebraically comprehensible. I want to make sure, hey, I need to remember this thing is negative. You just wrote a symbol that isn't negative. I got to account for that. It's a piddling, tiny piece of minutia detail, and it's going to pick me up if I don't do it carefully. I just asked one of my other classes this because they're doing modeling and limits of modeling. So, has anybody gone skydiving? Okay, good. I'm not the only crazy person who doesn't want to throw themselves out of a plane. My parents went skydiving. For my father's 80th birthday, he threw himself out of a plane. He and my mother went skydiving. They went in Hawaii, where my brother lives. They went out and visited. They did a skydive in Hawaii. If you throw yourself out of a plane, you start falling. You start falling faster and faster and faster, right? That's how gravity works. Do you keep falling faster and faster and faster? Not forever. Why not? I'm sorry, what? I hit the ground. Oh, that's a bad idea. If I threw myself out of a plane from about 3 miles up, which is a legitimate skydiving altitude, 15,000 feet, I would only fall and continue to accelerate for about 3,000 feet, at which point I would stop going faster. Why? No, gravity itself doesn't change. There's something else that's happening to me as I throw myself through the sky. I'm not even talking about my parachute. I'm just... Friction. I have this wonderful thing that's slowing me down called the air. Air resistance. I'm getting pulled down by the force of gravity, and the wind is pushing back up against me. At some point, those two forces balance each other, and you are literally falling as fast as you can. It's called terminal velocity, and it is the limit as t goes to infinity of the balance of those two forces. The same thing happens when you start driving your car faster and faster and faster. If you floor it in your car, I don't want you to do this, you can probably hit 120, 130 miles an hour. Do you know what the land speed record for a car is? It's over 700 miles an hour. Why can't we keep going faster? The air pushes back on us. Eventually, you go fast enough that you cause the air in front of you to break. And instead of just parting the air around you, you punch a hole in it. You've heard this before. A sonic boom. If you crack a whip, the crack sound is the tip of the whip moving so fast it breaks the air in front of it. The fastest thing I can do with both feet on the ground is break the speed of sound. It's a limit. Useless. I'm never going to do it anywhere. Do you know why I care about the speed of sound? Because there's an Air Force base down the road. And if those jets go overhead breaking the speed of sound, then you shatter glass with the shock wave generated. Useless shit. I'm never going to do it anywhere. Don't build your house on the Latrobe Airport approach. So taking my limits as I go to infinity actually has a really practical use. More questions. I wandered off topic. Yes, because I know this number should be negative. This expression is positive, always. So I needed to make it negative to match.
What would it match?
It matches this.
Would that be 1 over negative? Or is that whole, like, 1 over x?
This is a negative number, right? 1 over x itself is less than 0 because x is going to minus infinity.
-4 minus 0x.
Well, the negative is outside the square root. That's why I put it here. More questions?
We don't have a problem similar to, section 4
2.4 question 7. We can actually do 247 if you want, since 7 is not one of the required problems, right? So that question says, limit as x approaches 2 of x squared minus 3x plus 4 equals 6. And then it says it gives me an epsilon, right? And it gives me 2 epsilons. So which one do you want to use first, 0.2 or 0.1? Okay, so if epsilon is 0.1, I want to know what delta is. Now, I am of the opinion that I like the pictures that we had in number 4 and the picture I drew for number 6. So I'm going to start with that same sort of picture. Out comes the graphing calculator. Let's graph f of x equals x squared minus 3x plus 4. And I really only care about what's going on near x equals 2, right? Sorry, not x equals 2. So I look at my standard picture. This is a parabola. It's an opening upward parabola. And there's 2. And I claim that the limit is 6. There's a typo here somewhere. There's got to be a typo here somewhere. 4, 4, 8. Because that limit's not 6.
Isn't it x cubed?
Is it?
That's what I thought of x first. Okay, I'm not.
Okay, I can't read.
Yeah.
My glasses need to be straightened. I apologize, x cubed. So let's change that. X to the 3rd Much better. That makes more sense. Much better. There's my picture. I think as I get closer and closer to 2, the y value should be closer to 6. So I'm going to say epsilon is 0.1. That means I could be 0.1 above or 0.1 below. If I'm 0.1 above, I'm at 6.1. And if I'm at 0.1 below, I'm at 5.9. Let's add those to my graph. Now, the problem is my window isn't very big at the moment, is it? I can't really see very much between these two lines. So I'm going to zoom in just around that spot. There. There's 2, 6, there's 6.1, there's 5.9, right? I want to know the x values where we cross. I could try and do this by hand, but I have a picture. So I'm going to ask the calculator, hey, where do these two things cross? By hitting the calculate button, second trace. Notice option 5 asks where two things intersect. Option 5. The first thing is going to be my equation. The second thing is going to be the graph, y equals 6.1. And then it says, hey, where do you think they cross? So I just move my x value over until I think it's close to where they cross. Hit enter a third time. Write that number down. That's the number that goes with 6.1. Now let's repeat this process, but this time instead of using 6.1, we'll use 5.9. Option number 5 for intersection. The first equation is the one I want on my graph. There, that's the equation. Hit enter. That's not the equation. So hit the down arrow to go from y2 to y3. That's the equation I want. Hit enter, get close to where you think they cross, and hit enter again. It's a little bit less than 2. $1.9888055. With me so far? Subtract 2 from each of those in absolute value.
So it said prompt here, but to find this out graphically.
Yeah, you see the
That's
little,
why we're not doing.
right, do you see the little symbol next to the number 7?
Yeah.
That symbol looks like a graph picture, doesn't it? This symbol right here tells me to do this using a graph. It's much harder to do this algebraically. Well, yeah, because then I'd have to solve a cubic equation. And I don't know the formula for that. There is one, I just don't know it. But now I'm like, oh, so in this case, if I subtract 2, I get 0.0110299. Here, if I subtract 2, well, in absolute value, I get 0. I can never do this one in my head. X minus 2, 0.111944. All right, which of those is smaller? There you go. The smaller one is delta. Ta-da! I am 100% in favor of doing things algebraically when I know how. Solving cubic equations by hand is not among that list.
Figure out how to build the intersection.
Ah.
So that's why I was like.
Hang on a second. Button, share, Chrome, share. On our Canvas page, click. One of my students from back in 2000 wrote this file, how to use a graphing calculator. There's a bunch of useful stuff in there. If you're going to do anything statistically oriented, there's a bunch of useful stat stuff in there too. If you have a graphing calculator that has a TI model, this should still be accurate. If you've got the color one, the pictures won't look anything right. But also the Education TI website, education.ti.com, guidebooks, all projects. Lo and behold, there is the guidebook for the TI-84 color edition. You want the manual? It's right there. This will tell you everything you want to know about this calculator. How to do anything. So if there's something on your calculator you've forgotten how to do, here's 2 different ways to find out how to do it. Third option is to come to office hours and bug the snot out of me, and we'll figure it out together. More questions?
You go back 620. Should you start that problem using a conjugate or just go straight into the 1/1?
2.623. Look at the difference between 24 and 30. In 30, I was going to end up subtracting infinities, right? But in 24, I'm going to end up with infinity over infinity, right? So in 24, there isn't some weird operation for me to try and fix with a conjugate. I can go directly to the 1/1.
1/2 divided by 1/2 square root of t squared.
Because we are going to positive numbers, yes. I need the negative on the square root part, the same way I did in number 30. But the only reason I need this is because we're going to negative infinity. In problem 24, we're going to positive. Notice in 30, I didn't do that until after I'd done the conjugate expression. And that's why I asked, what was the expression you had? It's division here. That's the reason I can do this part, because it's infinity over infinity. I'm being a little fussy here. I can add it in a couple different places. So I can think of saying, I've multiplied through the 1/x everywhere, yes? I don't have to use that negative until I bring the square root in over there. I don't have to deal with a negative until this tries to go into that. So I really only need to account for the negative sign when I introduce an expression that would otherwise be positive. And that's what I did here. This is a negative thing. The 1/x right here. If I write square root of x squared, that's positive. Fix the sign. So you really only introduce that negative the minute you bring in the square root symbol. Other questions? Yes, ma'am. 5. Chapter 2, section 5, yes? Okay. When it says use continuity, we had a theorem that said if my function was continuous, I could just plug in, right? So you need to tell me, Is this continuous where I want to plug in? Is this continuous where I want to plug in? Because I'm moving the limit from outside the sign to inside the sign. Then from inside the outside the tangent. And as long as I know it's continuous at every step of the domain, and you tell me why I know it's continuous, then you use continuity to evaluate the limit. Fortunately, once again, there wasn't a little graph someone said you had to develop the graph. You could, but you'd still have to justify the continuity part. The piece about composition is important because the fact that I'm moving inside other functions, I have to know the continuity happens all the way in. We call places where we have discontinuities, we call removable, essential. In general, they're called singular points or singularities. And what happens as you get to a singularity is really, really going to depend on what kind of a singularity you have. We just talked about essential and removable. There are other types. Essential contains other things. Well beyond the scope of this course, but weird crap happens at singularities. That's where the math kind of breaks. And you go, how do I fix this? And that's why they call them singularities for black holes. Because the equations we have in physics break at those spots. You're dividing by zero. You can't do that. Let's take limits and see if we can figure out what's going on. More questions. Ask me more, people. I got 20 more minutes with your name on it. Again. 3, 1, 2, 3, 4. So 16. Okay. I really don't have reasons to nail your asses to the chair. So if you still have questions on this or anything regarding this class, stay and ask them. Otherwise, this is due tomorrow. So I will see you then. I'm not going anywhere. This is staying up. I will continue to answer questions for people who stay. Otherwise, hasta mañana. Yes, ma'am. Okay, hit me anyway.
Like secondary math. If I wanna. Like specify non-calculus, but like statistics, so I still include all of those lots, taking case spots.
Well, we don't have a stats degree, right?
Yeah.
So the only way you get a stats certification would be to get it through a math degree. So yes, you'll take all the calculus stuff. And our problem stats classes are math driven, calculus driven problem stats. So yeah, you're one of us. Now, I do know that some universities have statistics specific degrees. And I know they change what upper level courses you take, but all of the intro prob and stats courses in math or in stats start with the first 3 semesters of calculus.
I was getting sure.
Yep. One of us, one of us, one of us. Gabba gabba, hey. Yes, ma'am. Yes. Sure.
Is that just, I do what I want, as long as I follow what's going on? With me.
As long as you hit this dot and hit that dot.
Okay.
Yeah.
Yes,
ma'am.
So I was looking at the schedule and it said, so the exams from 2.1 to 3.1,
Yes.
but we still have to do 3.2 homework.
That homework is not due because this section's homework, this will be the question answer. These sections will be due here. This section won't be due until here.
Okay, yeah, cause I was looking at it, those groups together.
No, the home, if it looks like that on Canvas, I made a mistake. 3.2 should not be due here. 3.2 should be due here.
Is due with 2.8. 2.7, 2.8, 3.1, 3.2, they're all due September
Let's
19th.
fix that, because that ain't right. Assignments. 3.2, you're right, that's wrong. 19, 19, 19. This one should be due on the 29th. Edit.
Okay, yeah, cause I was like, oh, it's so consent.
Nope,
Trying to like study ahead, so when you're like. explaining
29.
things, understand better.
Why didn't that change? Edit. September 29th, save, reload. There. So 29, 29, 29. There are 3 due on the 29th. 2, 3, and 4. Yes.
Thank you.
Thank you. Good catch. Yes. How about
So-
answer?
This one, I understand. I like to set the graph up
Yep.
so I could see it. So I got to my answer here and it says X is less than
Yep.
this, but it's greater than that. How? Like,
Because this function
Mhm.
is not linear.
Okay.
It's decreasing instead of increasing. So your inequalities switch order when you do the inverse cosine.
Okay. So even though,
Right here, those will flip direction.
so do I need to flip these?
Yes,
Okay. So that's, and then it'll match up with the graph.
exactly.
Okay. And then I had one other
That's what
one.
happens when your function is not monotone the same way you want it to be. That's why I tend not to set them up that way and do them more like this, where I set up each one separately.
Okay. And then for.
Push the button. Push the button. Thank you. I gotta make the thing come back.
For this one, I might need to borrow the book real quick because it's off a graph for number 4. It's page 137.
Page one, what?
137.
This should be page 137. Yes.
Okay. Yeah, so for that one, so X approaches positive infinity 2. Yeah, okay. And then negative infinity, I got -1. I'm good with those. Okay, so for the asymptote, is y equals 1 one of them?
No,
It's not?
no, because as I go out, I don't know, well, it might be a place we avoid,
Mhm.
but there's no reason given as to why we should avoid it, right?
Right.
The fact that we miss a bunch of stuff doesn't make that an asymptote.
So is there any horizontal?
Yeah, what happens if we go that way? Do we have a
It-
limit?
It doesn't hit -1.
Well, that's an asymptote. That's the value we're settling down on.
Even though these cross -1?
Yeah, absolutely. Remember, we're only really considering what's happening that way.
Okay,
We're only really considering what's happening that way.
okay.
Even if we cross it, we're settling down to it.
So is y equals 2 in asymptote?
As we're going, as we go off to the right, that's what happens. Isn't it?
Even though it crosses it?
Yeah.
-2? Okay,
Like we were talking about the pendulum, it settles down to it. right?
okay,
Our asymptote is, the root word of asymptote is symp, like sympathy, to be like something. So we're getting like that horizontal line as we go.
so it doesn't matter if it crosses it.
Correct.
Okay, and then our verticals are
Yes,
0.
vertical asymptotes we don't cross.
0 and 1.
Yep.
Okay, all right, that
And
makes,
not one.
sorry, 2.
Okay, good.
Okay, perfect.
Yeah.
Thanks, that makes sense.
Thank you.
So
Yes, sir.
for number 30, following what you did on the screen, everything else, everyone over X, so then I get 3X over 4X squared over X squared plus. I can't remember. 3X minus 2X. And then obviously those 3X's cancel out, and so those X squared.
This X, what happened to it here?
Is it? 2X over X,
Which would just give me,
so it's 0.
2X over X would give me,
Wait, because the X's would cancel out.
and I would get
Yeah, so
left.
then I would have to, I just mean over here when I eventually get to X.
Well, I'm worried about the what happened on top, right? Isn't there an X on there too?
Yeah, okay, but let me.
Okay, good plan, good plan, good plan.
I don't think
It's just like.
As, okay, at 0, we should hit 0. So I should go through that dot right there, 0, 0. As I go to 1 from the left, I should go to infinity. As I go in from the right, I should go to minus infinity.
Okay, so this one needs to go down that way.
Yeah,
Okay.
as I go out to infinity that way, I should go to -2. As I go out that way, so
Okay.
this piece is upside down and you didn't quite go to the
Okay,
right
so
dot.
then it needs to go like that.
Well, except we don't cross that line, right? Because we still have that asymptote there.
Okay, so like.
Yeah,
Okay, thank you.
you're welcome.
I just have a question about like the calculator.
Well, let's hope.
Because
we
happening
do.
sometimes, like whenever I put in just like 6.1 as an asymptote, nothing comes up.
Okay, because if I go back and I look at your y equals menu, you see all those highlights, those are highlighted,
Mhm.
the equal signs. So if I go down to the equal sign and hit enter,
Okay,
that turned it on.
okay.
Or should have turned it on. You're in a different graphing mode.
Oh.
Why are you in a different graphing mode? Let's change those. The hell? No. Motion God, silence, yes, feels the way something going. I don't know what that graphing mode means.
Is it on the, I can look if it's on the website.
It should
Like
be.
you were saying.
Because if you look. See, there are three graph things you've got here. That one's got the little vertical bar on it, right?
Uh-huh,
That one doesn't. And then that one has this funky looking double triangle on it.
yeah. I can look at the website.
Yeah,
thing.
I don't know what that does,
Okay,
because
I'll
on
look at
mine, it's got a different piece on it. It's just got a little diagonal line.
Yeah, no, that.
So I'm not sure what the graph
I'll look at-
setting is.
I'll look on the link you have.
Please, thank you. Yes,
Right. I don't understand this one at all, because that's a discontinuity.
yes,
It can't ever be continuous, so it can't fall to that intermediate value here.
correct.
So then how can we draw a graph that does satisfy?
It satisfies the conclusion of it. It doesn't satisfy the theorem. It satisfies, we happen to hit 2 this time,
So this one would satisfy,
because it hits 2,
and this one wouldn't.
because you missed 2. There you go.
That's a terrible question.
No, it's a question that really makes you think about what it means to satisfy the conclusion of a theorem, as opposed to satisfying the theorem itself.
It actually right at the bottom, it's like the hypothesis that just threw me.
Ah, so the whole point is that our hypothesis for that is our function is continuous. When our function is continuous, we're guaranteed to satisfy. But if our function is not continuous, we could still satisfy the conclusion. So
Just because it's not guaranteed doesn't mean it can't.
the following is a true statement. If the moon is made of green cheese, then I'm standing on the ceiling. Isn't that absolutely bizarre? If I have a full head of blonde hair, then I am also female. That's a true sentence out of my mouth, because it started from a false premise. If it's all from a false premise, it could be true or false. The conclusion doesn't matter. Then it only works if it's true. No, this is logic. This is logic we should have learned in geometry a long time ago, a galaxy far, far away. I understand. But what that really is pushing at is I'm pushing you to think about what an if-then means. And the whole point here is I didn't hit the if, I can still hit the then.
Or if you're given a then. And you're questioning it.
Mhm. Yes,
I think,
that's about converse and contrapositive as
I
well.
think I wrote this one out correctly.
I hope
When
so.
we went and we redid it,
Yeah.
I'm still confused with that.
Okay, so this site right here, when you write 1/x and 1/x, that's perfectly fine. When you bring that in here, this is now a positive thing. This move, bring the 1/x in as over x squared, that's the part that's wrong. Because you just told me 1/x is positive when you write it like that. But when you write it like that, you've corrected for it.
But if the negative is in there, then
It's
it's.
not inside, it's outside. It's not inside the square root, it's outside the square root.
I just don't understand why the negative appears in that step and nowhere else.
Okay, because when I write this is a positive number. When I write this, sorry, this is a negative number. Because we're going to negative infinity. This is a negative number.
Yes.
When I write this, this is negative. This, that's not negative. When I go from here to here, I changed signs.
Okay.
That's not allowed. So to balance that sign change, I do that.
Thank you.
You're welcome. At some point you'll go, oh, and then I'll be happy. Talk to me.
So you just explained this one, but
Yes.
I still don't. So I wrote down like, it was for 36.
Uh-huh.
So you said to pretty much remove this and like. I don't know. like,
Okay.
plug it in.
Yeah, I'm gonna move it inside because we have this rule here. I think it's theorem 9. Whoop, don't fall down. In our discussion of continuity, we have this result. Yes. Theorem 8. If G is continuous and F is continuous where G spits out, then I can move the limit from the outside to the inside. See how your function has the sign on the outside, the tangent on the
Yeah,
inside?
so that would be.
So I move it in. And then I say, hey, wait a minute, inside that tangent, I've got a cosine, right?
Yeah,
So let's move it in again. But then I have to check.
so move the limit in.
Yeah,
So. If I plug, like, I would be plugging in like pi over 2 into the cosine.
well, let me actually write it out. I'm like limit theta goes to pi over 2 sine of tangent of cosine of theta, right? I said move it in. So I'm saying this is sine of limit
Oh.
tangent cosine theta. Theta to pi over 2, right? So this is what theorem 8 says. Theorem 8, that I can go from here to here. But then I can do it again and go from there to there.
Okay,
And then you can say, hey, wait a minute, cosine's continuous, I can plug in. And then I look at this number and I say, is tangent continuous there? And if the answer is yes, then I can plug in. Hey, is sine continuous at whatever number just came out? If the answer is yes, then I can plug in. And I go plug in, plug in, plug in, and poof.
so I plug it in at cosine first and see if it's continuous.
Right. And see if the tangent then works there.
So do I just like plug in pi over 2?
Yeah. What's cosine of pi over 2? But that's really what you have to look up, right?
Yeah.
Right.
We had to memorize it.
Yes, at some point you should have that completely able to recite.
So let's visualize it like that.
Okay. You know the hand trick? 0, 30 degrees pi over 6, 45 degrees pi over 4, 60 degrees pi over 6, 90 degrees pi over 2. Do you want to do cosine or sine? Start here. 1, 2, 3, 0, 1, 2, 3, 4. No, cosine. Cosine is 0, 1, 2, 3, 4. So which angle were we doing? Pi over 2, right?
So that was 0.
Take the square root of that number, divide by 2. If we'd done 45 degrees, it would be 2, right?
Yeah.
Square root of 2 over 2. Square root of 3 over 2. Square root of 4 over 2. Cosine of 0 is 1. I carry my unit circle with me right here on my hand. Sneaky mother that I am.
So.